Everyone who has ever played Portal has created a portal configuration where anything can fall infinitely. But where does the energy for this come from? Do portals just create it out of thin air, letting you build a perpetual motion machine? Yes, because this is an example of incorrect naive gravity in a universe with portals, which assumes that at every point gravity points downward, regardless of the position and orientation of the portals. But in reality, portals should bend or teleport gravity. And here's what it looks like. With this kind of gravity, you can't create a perpetual motion machine, and it doesn't violate the laws of physics. But why? And what do all these arrows and colors mean? I know none of this makes sense yet, but later I'll explain what is drawn here and how I calculated it. What equations make it work? What criteria the correct gravity should meet? How this gravity affects the world and objects in different setups? And of course, we will look at how this affects the most debated portal physics question, and what kind of gravity we get in that situation. And specifically for this video, I programmed a pretty complex physical simulation that calculates not only gravity with portals, but also how it affects a physical object. So everything you will see later comes from actual calculations, and not just my speculations. But the most interesting thing happens with gravity in 3 dimensions. As for the inside, wait, what is this? You solved gravity for 2D only, and this is the sponsored dimension. Oh, I'm good, thanks. Just give me a minute. Well, fine, since you closed the portal. This video is sponsored by boot.dev, a platform where you learn backend development in Python, SQL, and Go by actually building things and writing a ton of code. Well, everyone has basics, but are there any in-depth lessons? Yes, for example, have you ever wondered how memory in Python actually works? They have a course on writing your own garbage collector from scratch in C. Sounds like it's all pretty hard. But you like puzzle games, right? On boot.dev, learning is gamified too. XP, achievements, boss battles. And there are memes in the lessons. I also really enjoyed their course on building an asteroid game in Python. Sounds interesting, but I don't know. All lessons are free to read and watch. If you are interested, go to boot.dev and you can use promo code Optozorx for a 25% discount. Okay, I will take a look. How can I leave this dimension? I've opened the exit portal behind you. You might be asking, why is such gravity incorrect? What exact law does it violate? It breaks one portal axiom that I introduced in this video. I recommend watching it first. But for now, let me briefly remind you what it is about. We are considering portals that don't just teleport you from one place to another through some kind of scanning and reconstruction devices, but portals that bend space itself in such a way that this space bending looks like a teleportation. Sort of like how wormholes work. They connect distant parts of space close to each other in a higher dimension. The special thing about this model is that now the portal surface is just a way to make a cut through this space bending. Because if you take such an elongated portal surface, the final space bending still converges to the same shape as with a flat surface. And if you want to shine a flashlight near a flat portal, the light ray will arrive at exactly the same place as for this semicircular portal, because first it teleports through the orange portal, then returns back. So just by looking at it, it is impossible to tell what the shape the portal surface is. For any surface, it will look the same. Or you could say that this surface simply does not exist. And this space-bending model can be reduced to a pretty simple axiom that a portal behavior does not depend on the shape of its teleporting surface. And now, how exactly does naive gravity violate this axiom? Actually, this portal setup obeys it, but it still violates the law of energy conservation. Therefore, let's look at another scene. Here, an object goes into the blue portal and emerges from the upper portal. It falls straight down, everything makes sense. At every point, gravity points downward. But look, at this moment, on one side of the portal, gravity acts downward on the object, and on the other side, it acts leftward. And that's exactly where the problem for our axiom lies. Let's take a semicircular portal surface. Here, gravity points downward at every point too. But now, when the object enters the portal, it will feel downward gravity longer than leftward gravity, and will end up arriving at a different place. So, you get a different result in each case. Yes, you could say this depends on how I program portals, and I could make gravity point leftward here. Then everything will work the same. But how will you find the place where gravity should make a sharp turn on a continuous space bending? There are no portal surfaces here. So let's figure out how we can actually teleport gravity so that it doesn't break this axiom and stays consistent. To understand how to teleport gravity through portals, first let's remember what we know about it. The key thing is that its force can be calculated using Newton's law of gravitation. It works for two-point masses separated by some distance. And when we look at this equation, we can see its main problem: distance. It is clear how to measure the distance between 2 points when we have an infinite flat space. But what if we have portals? In that case, we have regular distance r1 and we have distance through portals r2. Which one should we choose? Or take this case, where there is a portal between the objects. In any direction, there is no direct path from one object to another, because the portal blocks the path. Then should the distance go around the portal? All this is unclear, and this makes it hard to calculate gravity with portals. One of the first solutions that came to my mind is to imagine as if there are gravity carrier particles, gravitons. They constantly stream out from any mass and go in all directions. And when they reach another body, they give it a pull directed back towards where the graviton came from. This model can be tweaked to give the same results as Newtonian gravity. And it's pretty easy to plug portals into such a model, because in that case, they should just teleport gravitons as shown here. In this case, you get a bunch of very sharp gravitational shadows from the portals, which means the body will feel abrupt changes in gravity. And behind portals, there won't be any gravity at all. Meaning, in this model, gravity doesn't go around the portals. I abandoned this model and didn't develop it further, but I wanted to show how it could work since most of you probably had the same idea. Before I explain the next model, I want to show the visual language of all the following simulations. So here's a planet with some mass, where white means no mass and gray means there is mass. This planet creates gravity, which is calculated trivially by Newton's law. To make things easier, from now on, we won't talk about the gravitational force between two bodies. Instead, we will talk about gravitational acceleration, which only depends on one mass. Basically, it is the force that an object with a mass of 1 would feel at any point in space around this planet. The color shows how strong the acceleration is. Dark color means weak or zero gravity, and yellow means 1g. We can make the mass 10 times bigger, and then we get a gradient of red and white, where white is 10g or more. You can see that outside the planet gravity changes predictably, and inside the planet it smoothly decreases to zero as you get closer to the center, because parts of the planet's gravity cancel each other out. Next, we can add arrows that point in the direction of gravity. And we can make the arrow size represent the strength of gravity at that point. Next, let's add another small planet, and their combined gravity will look like this. We see a place between planets where their forces balance and gravity equals 0. If we increase the small planet's mass, this point will move, and the gradient will change. But arrows aren't very convenient, so instead I'll use these streamlines. These are idealized movement paths that make it easier to see where gravity points. I won't show them in animations because they flicker a lot, as you can see. By the way, the gravity gradient here is actually continuous and smooth, but I am using just a few colors to make its shape easier to see. And to finish off this visualization, here's what a falling object looks like with two planets. The planets have the same density, so it is attracted to the larger one and rolls on its surface. By the way, if you create a small object in the center of this spot, then with one offset it will fly one way, and with another offset the other way. So it's not quite accurate to say gravity here is zero, rather very weak and unstable. And now we need to get familiar with the new concept. The gravitational field we looked at has direction and force at each point, meaning it has two numbers at each point, and is denoted by the letter G. But in physics it's more convenient to use another quantity, gravitational potential, which is denoted by the letter phi. It shows the potential energy of unit mass at each point. So at each point it's just one number. For example, here it's 0 and here it's 0.07. And the relationship between potential and gravity is that gravity is always directed towards the decrease of potential. In other words, if you picture the gravitational potential as a landscape, then gravity at any point is just the direction a ball would roll downhill. Or if you know these words, gravity is calculated as minus the gradient of potential. So they are totally interchangeable and you can always calculate one from another. But why do we need this? Look, besides Newton's law, there is another, totally equivalent way to describe gravity using potential. They often teach about it in university, and it's called Poisson's equation. It looks like this. It lets you calculate the potential phi from the mass density ρ, and p and g are just constants. We won't go deep into what it means right now, just know that it exists. To oversimplify, this equation says the potential at any point is the average of the potential of its infinitely close neighbors. That is, each point in space depends only on its surroundings. Now look, if you take a mass distribution like this, plug it into the right side of the equation, and then solve it, you will get the potential for the entire area. And from that, we can calculate the gravity with its direction and force. And there are no distances in this equation. It works on infinitely small patches, which means we can calculate it on literally any space, not just flat one. Therefore, we can use it to calculate gravity with portals. And as we remember, portals bend space in this interesting way, which means we can try to calculate gravity on such curved space using Poisson's equation. And this picture right here shows what gravity looks like on such a curved space. But you might ask, how did I calculate this? I'll talk about this closer to the end of the video, but the short answer is I used a numerical method called the finite element method. But I want to clarify right away that I calculated all this for a flat 2D world. And the result will be slightly different from our volumetric 3D world. But the differences are not fundamental. Before we move on to the experiments, I want to clarify an important detail. According to the theory of relativity, gravity is the curvature of space-time. So some of you are probably thinking that since our portals bend space, they should also create their own gravity. Actually, no. First, we are not considering Einstein's theory of relativity. Poisson's equation describes Newtonian gravity. Second, portals bend space in such a way that it remains flat. Yes, that sounds absurd, but it's too much to explain here. I'll make a separate video about it someday. And most importantly, if I put two portals in my simulation in a vacuum with no other masses, no gravity will appear. It will be 0g everywhere. That is, portals don't create their own gravity. They just bend the gravity that's already there. Okay, now for the experiments. So right now we are in the Earth gravitational field. Gravity points down and the force is 1g. Okay, we create one portal on the top and another on the bottom. Right now I have gravity teleportation turned off. I want to show how this works in a typical game with portals, using that naive incorrect gravity. Our portals are two-sided, so if we create a cube at the top, it will fall to the floor through a short path. But if you spawn it in the center, it will fall forever and keep gaining speed forever. And this will only be limited by air resistance. And now we calculate gravity using Poisson's equation on the curved space. This is what it looks like for these portals. A lot has changed, so let's go in order. Here we are also in the Earth gravitational field with a force of 1g, which is represented with yellow color. Above and below the portals, we see that gravity has become a little stronger than 1g. We place a cube on the top and it falls just like before. Now for the most interesting part. What if we release a cube right between the two portals? It first falls down, then up, and down again, and then it gets pushed out. And looking at the streamlines, this is exactly what we'd expect. Now let's create an object above the bottom portal. It gets pushed out to the side immediately, just like the streamlines show. But up here, near the top portal, the lines point upward. Does that mean the object will be sucked in? Let's run it. Wow, it really is. And I want to clarify that I spawned this object with zero initial velocity. This is genuinely what happens. And if you spawn it a little lower, the pull isn't strong enough to suck it in. Next, I want to show you how these portals affect objects a little further away. If you create the object here, it gets attracted to them. But if you spawn it below the center, it is pushed away. Next, we can make a visualization like this. Here I created a lot of independent particles in different places. When I start the simulation, they will fall at the same time. Starting and pause immediately. Notice how aggressively the bottom portal repels all the particles. Continuing. So from this we can guess that the air at the edge of the bottom portal would get pretty thin. But what about our favorite infinitely falling cube? Is it impossible after all? Actually, we can still do it. We need to create a cube with some initial velocity, which I depicted with this white arrow. It flies and doesn't seem to stop. But the trick is that it is not gaining speed. There is no gravity here to speed it up. So here it's just flying on inertia. In some places it speeds up a little, and in other places it slows down a little. But its energy remains constant. Kind of like a pendulum that swings back and forth, speeding up and slowing down under the influence of gravity. This is related to a similar idea about extracting infinite energy from such a portal, using water falling under gravity. But as we see, in honest physics, this won't work. So sorry trolls, no perpetual motion machine. But what's even more mind-blowing, you can create a cube that is initially flying upwards. And it will do it till the end of time, if we don't consider air resistance. If I enable it, it will be thrown out from this loop. So with real gravity, there is no infinitely moving cube through portals. It will always fail at some point. The next thing that might be bothering you is what's happening at the edges of the portals. Here gravity grows really strong, to red and then to white, which is 10g and more. Does it go to infinity? I can't calculate this analytically, so I don't know for sure, but from my experiments, it looks like it. We already knew that the edges of a portal are infinitely sharp knives that can easily cut any object, but now infinite gravity is added to the mix. That's why I'm putting walls here to protect objects from these edges. And when object falls on this wall, it just bounces off. Now if we zoom out, you can see the portals only distort gravity right around them. Their effect doesn't reach out to infinity. Furthermore, as we remember, portals bend space in such a way that it looks as if we glued space together in the portal area. And on such space bending, the gravitational field looks continuous. The short path section has become connected, and the section where the object gets stuck in a loop looks like a small, separate cylinder. And you can clearly see the portal edge point where gravity gets very strong. Next experiment. Now let's move the portal sideways. The gravity changes somehow. The streamlines show that objects are now attracted slightly to the side. Nothing unusual is happening here. But what's really unusual is if you raise the portal up. Look, the spot under the orange portal becomes redder, which means gravity is getting stronger. And if you lower it down so that both portals are at the same height, the portals stop affecting gravity. Very interesting. So the effect portals have on gravity depends on the height difference between them. Yes. Look, for a gravitational field without portals, the acceleration of free fall is 1g everywhere. But the potential increases from bottom to top. And when we add portals here, they force the potential to be equal at every corresponding point along their surface. And when we raise one portal, at every point of the portal, the potential from above and the potential from below must be equal. But at this height, the potential wants to be different. And Poisson's equation tries to compensate for these conflicting factors and eventually converges to a state where gravity changes in this strange way, getting stronger in one place and weaker in another. And as I already said, there is a very direct link between gravitational potential and potential energy. To get energy, you just need to multiply the potential by the object mass. This explains why we couldn't create a perpetual motion machine. An object has fixed potential energy, and the gravitational field can't do work to accelerate more than what's contained in this energy. That's why I consider this gravity to be correct, because it doesn't violate the law of conservation of energy. And to demonstrate this even better, let's take two portals that are facing each other on the ground. We will create a ball and shoot it towards the portal. It loops in this space. Now what if we place one portal higher than the other and tilt the ground? For now, I'm not teleporting gravity, so this is the case of incorrect naive physics, like in the portal game. In this case, the ball accelerates indefinitely, and this is another perpetual motion machine. Here, the field is doing work because the object constantly gains potential energy when it teleports and it is converted into kinetic energy. And now I'm turning on honest gravity teleportation. When the portals are at the same height, they don't do anything special. But when the height changes, the gravity also changes. After we release the ball, it rolls down and then back up, and after wiggling back and forth a bit, it settles and stops rolling. And as you can see from the streamlines, it should be pushed into the tilted ground. And once again, no perpetual motion machine. But did I really do everything right? Maybe there is a fundamental error somewhere. Let's check this against the portal axioms. Let's start with the axiom that the behavior of a portal does not depend on the shape of its surface. We change the shape of the portal and see that the field doesn't change at all. And I am not just changing the picture here, I'm really plugging different portal shapes with different triangulations into my simulation, and every time it converges to the same picture. The next axiom is that portals should behave exactly like a doorway when we put them back to back. Let's try it. We start from a familiar position and gradually connect them. You can see that the effect on gravity gets smaller and smaller until it becomes zero. So this axiom also works for gravity. The next axiom is the portal merging axiom. It states that if you seamlessly connect two portals, they will behave as one portal. I used this in my first video when I explained how to calculate a portal in a portal, or in another video when I showed how you can create a triple portal from 3 doorways. We can check this by putting two pairs of portals next to each other. We see that at the edges there is this increase in gravity, and when we gradually connect the portals, we see that the inner edges start to get weaker and weaker until they disappear completely. This axiom also works. And the last axiom I just made up. It states that the smaller the portal, the less it should affect the outside world. In theory, this sounds logical. Let's check it. We are shrinking the portal 100 times. It doesn't look like the gravity teleportation has become 100 times weaker. Let's make the portals 10 times more smaller. Almost nothing has changed. Another 10 times decrease. What is going on? Why does the influence on gravity remain so strong? Currently, portals are 10,000 times smaller than previously, but their influence on gravity is still very strong and noticeable from a large scale. What is happening? Does this mean that if we have a portal the size of an elementary particle next to a black hole, it could tear the Earth apart? Actually, I'm not sure why this is happening. It is probably related to the fact that I am doing these calculations in 2D, not 3D, because dependence of potential on distance is slightly different there. In the end, most of the axioms hold, except for the axiom about size and influence on the world. So it seems like my approach is correct, with a small disclaimer that it all needs to be rechecked in 3D. Okay, with that settled, let's finally get to the physics question. What will happen if a piston hits a stationary object? Will it just slide down because it had no initial velocity, or will it fly out because the piston gave it velocity? First, let's look at naive physics without gravity teleportation. This is how it will work for a flat portal. The object will fly out. That is, it will behave like option B. If you want to argue, watch my previous video where I explain how the portal axiom affects uniformly moving portals. And this is how it will work for a semicircular portal. Nothing will happen to the object, and it won't even slide. So this isn't even option A. And now we turn on gravity teleportation. In the flat portal version, almost nothing has changed. The object flies out just like in option B. But in the semicircular portal version, look what happens. The object slid off. That's a one-to-one match with option A. Insane. All my life I believed that option A was absolute nonsense. But when you see something like this in a simulation, it's hard to argue. So it really seems this scene was missing gravity teleportation. But why does it behave differently depending on the portal's surface? We have an axiom that the behavior of portals should be same in both cases. As I said in the last video, the culprit is the fact that the portal stops. It is the acceleration from the portal stopping that causes the problem between the different surface options. To prove this, I want to show what the scene looks like if the piston keeps moving and teleports the platform. So the portal moves, the object comes out the other side and behaves quite predictably. For the semicircular shape option, the same thing happens. And if you overlay them, they turn out to be identical. And another way to make the portals behave the same for different surfaces is to make the piston move very slowly. Then, for a flat portal surface, the object will slide off before the portal stops. And of course, it will behave identically for the semicircular surface as well. So I wasn't wrong when I said earlier that the answer in this picture also depends on the speed of the piston, because at such a low speed you can get A from B. So just as I said in the previous video, to fully resolve this issue, we need to go into the theory of relativity and develop a model of accelerating portals with gravitational waves. But actually, such a model already exists. A scientist who works on theoretical physics in the field of quantum gravity came to my Discord and developed the following model, where an accelerating portal must create its own gravitational field and consequently gravitational waves. In his model, the accelerating portal attracts the object. And look at this interesting thing. When the object is pulled in, it is in two places at the same time. This happened automatically and is due to the quirks of the theory of relativity. He even described it mathematically. Maybe one day I will have the energy to make a simulation based on this model, like I made this gravity simulation. Well, now, as promised, how does this finite element method work? And most importantly, how did I implement portals in it? I want to briefly explain this So the main idea is understandable even to a high school student, without deep diving into mathematics, and using very specific values. So first I'll explain how to calculate the gravitational potential when we have this round mass. Then I will add portals and show you what we need to change in the calculation scheme to make it work with them. So Poisson's equation is an equation that relates two functions, phi and rho, where rho is the mass density function and phi is the potential value function. They take two numbers, which define the coordinates of a point, and return one number, the value of the function at that point. And this equation shows the relationship of these functions at every point in space. The difficulty with differential equations is that writing down the final function mathematically is incredibly hard and sometimes impossible. But we want to solve this numerically on a computer, and computers can't store and calculate infinitely many points. So what do? The first stage is discretization, that is, breaking up space into a finite number of elements. That's why the method is called the finite element method. In this case, there are triangles, and there are 152 of them here. We ourselves decide how to divide space into these triangles. Next, we are only interested in the value of the potential and density functions at the nodes of these triangles. And there are 89 of these nodes here. And the specific result of this discretization is this diagram. We have 152 triangles, 89 points, and their coordinates. And each triangle is numbered and points to 3 nodes with a specific number. We will need this information later. Now what to do with the rest of the infinite set of numbers between the triangles? Look, inside each triangle you can get an intermediate value using all 3 numbers. If you just imagine as if they are on a single plane. I won't say how to write this down mathematically, but this method can be described like this. This triangle function takes the current coordinates x, y as input, then the 3 coordinates of the triangle, and then the 3 values at the nodes of this triangle. And this function returns one number, the potential or density at that point. Inside the triangle, it gives an intermediate value, and outside the triangle, always 0. Then the density function can be represented as the sum of this function over all these triangles, from the 0th triangle to the 151st. And in this function, we know everything except the current points coordinates x and y. Similarly, we can write this for the potential, and the only thing that will change is that we will use the potential values at the nodes, and that we don't know these values, so the function also depends on them. So we get such piecewise defined functions. So we have reduced the problem of finding an infinite set of numbers to finding 89 unknown numbers. How do we find them? Well, the first instinct is to take the Poisson's equation, take our piecewise defined functions, plug them in, and somehow solve it. The direction is correct, but it won't work naively. To make it work, you need to use complex math called the Galerkin method, which I won't go into. If you want to understand it, this topic is explained well in this video. The Galerkin method takes our discretization and Poisson's equation and turns them into a big system of linear equations. Here is an example of such system. To solve this, you need to express one variable in terms of another, and then substitute it into the other equation. So the solution can be found quite simply. In systems of linear equations, there is no multiplication of unknown variables, which means you will never get quadratic equations and so on. That's why they are fairly easy to solve. And here is what we get specifically. There are 89 equations and 89 unknowns. The unknowns are marked in red. Any school student with a calculator could solve this system of equations. It would be long and tedious, but they could solve it. And after using child labor, we get these values. Some potential was found at each node. Now we plug them into our triangles and visualize the potential. This is what it looks like. And this is what the gravity looks like. Of course, this is a very rough approximation, because there are few triangles. But if we take more and more triangles, the solution will get more and more accurate. Just look at how smooth this looks with 2 million triangles. And once again, briefly about the finite element method. We break space into finite elements. Then, based on them, we assemble a system of equations using the Galerkin method and solve it. And then we can use the calculated values to visualize the potential. And from this potential, we can calculate gravity. And of course, I've omitted a huge number of details to make the explanation simpler. You can learn all that yourself from other sources. But what I've described is how to calculate the gravity of a simple object in flat space. We are interested in portals. How do we put them in here? What should they teleport? Actually, it is criminally simple. Here we have added portals to the triangulation. They are marked in red. And here I've colored the triangles above and below the portals for convenience. Next, remember that portals are just some kind of space bending. And if we place this picture onto this space bending, we see that the green triangles should end up next to each other, and the same with the blue ones. What does this mean for our method? Let's look at our discretization scheme. First, we explore normal space. Here each triangle in its corner uses the same unknown with index 43, because it is the same point in space for each triangle. Now let's look at this green triangle. It's built on 3 unknown nodes with indices 73, 13 and 14. And the blue triangle next to it also uses unknown nodes 13 and 14. That is, they have common unknowns across this edge. But from the portal space bending, we see that the same point in space is between the green triangles. But they refer to different indices. This means the common unknowns should be between the green triangles, not between the green and blue ones. So we just rewrite it for that green triangle, so it has the unknowns 73, 18 and 19. Then when we place these indices on the curved surface, the green triangles will share the same unknowns. And likewise for all other points in space. And the potential equation is the sum of all triangles, where each triangle specifies which unknowns it uses. And that means for the triangles next to the portals, we need to change these unknowns. Yes, all the portals do is just rearrange the indices of the unknowns in each triangle a bit. And that's it. And then we perform the same operations to assemble the system of equations using the Galerkin method and get a different system of equations, which can be solved. I decided to visualize how the system with rearranged indices differs from the original one. And here the differences are shown in green. A few equations changed and a few indices in other equations. But otherwise, most of the equations remain the same as before. Then we solve the system of equations and end up with this gravity. And this is what it looks like if we increase the precision. And this is exactly why Poisson's equation shines here, because it's local. It allows us to recluse space like this, and it still keeps working and gives reasonable results. Fun fact, in university I studied at the Faculty of Applied Mathematics and Computer Science, and our main program was actually programming the finite element method. But at my last job, I was a regular backend developer. And now that I've quit and become a blogger, I'm programming the finite element method again. Does this mean I'm actually working in my field of study? And this soft object is just a collection of particles that are connected to each other by springs. And each particle is affected by both the springs in this body and our gravitational field. This approach is called a soft body, and here's an example video where they implement this kind of physics from scratch. Next, I want to compare my results with the results of other people. I found 2 sources where they solved this problem. The first was made by Zeno Rog, known for his work on hyperbolic geometry. He also made a model based on gravitational potential, and he got the same result I did. The character is repelled from the bottom portals and pulled into the upper portal. The next person who worked on this problem is Greg Egan, the author of cool sci-fi books. And for his book, The Book of All Skies, he also calculated gravity through portals and wrote a whole article about it. And he has this illustration with portals in different worlds and one source of gravity. I replicated this in my program and I got a very similar result. But it is still different because Egan calculated gravity for the 3D case and I did it for 2D. Oh, and also people from my Discord also got roughly similar results. Sarah and BBOB9764. You guys are awesome, thank you. And there's a ton of stuff that didn't make it into this video, how gravity behaves with portal in a portal, whether this can work for scaling portals, and what happens to gravity in a pocket dimension. If this topic is interesting, I can make another video about all of this. And if after this video you want to play with this portal physics yourself, move portals with your mouse, change gravity, affect this off-body object, and see different situations without waiting for the next video, you can do all this in the program I wrote for this video. I used it to render all the animations shown here. It took me over 200 hours to write this program, so for now I am releasing it only on my Patreon for all paid subscribers, starting at $1. And in the meantime, I want to give a huge thank you to everyone who is already supporting me. By the way, I spent an unhealthy amount of time on these animations, but I don't regret a thing because they are just too beautiful. And I also made a separate video where I explain how to create scenes in my program if you want to make your own simulations. This video is on my second channel. Well, that's all from me. Thanks for watching.